This video is an attempt to recreate an activity that we would be doing together in class to help remember what is happening when a nerve conducts an impulse, in particular with a cholinergic synapse. So in class we would each be assigned a little item here and work together, but unfortunately we don't have that opportunity now, so I'm just going to kind of try and go through it and show you what we would do. So this drawing that I have here is supposed to be a neuron. This is the cell body. Imagine that there are dendrites on it. I just can't fit them all on this, this image. And then we have an axon, and then these are our telodendria and our axon terminals. These are little vesicles inside our axon. And then this is our synaptic cleft here, and this is another cell, and we'll learn more about that in a little bit. But we have some different items representing things. We have a little rubber duck, which is going to represent a ligand. A salt shaker is our sodium. A banana is our potassium. We have little cows that are our calcium. And then some coelacanths, which are our acetylcholine. So at rest in our neuron, all of these gates, all of our channels are closed, and we have a resting membrane potential, if you remember, of -70 millivolts. What happens to transmit a signal is our dendrites, so remember we're going to pretend there's there are dendrites coming off of here, but our dendrites will pick up some information, pick up a signal. In this model's instance, we are going to have a ligand bind to the dendrite, and that chemically gated channel is going to open as a result of that binding. Now remember, when we are at rest, the potassium is located inside our cell membrane. Sodium is located on the outside of our cell membrane. So we are going to bind that ligand, and sorry, I got to get more sodium here. In this instance, this is a sodium channel, so sodium is going to flow into the cell. That's going to cause a depolarization of this membrane. The membrane potential is going to become less negative. This creates a graded potential. Remember, graded potential, the further we get from the stimulus, the less the depolarization is going to be. If the depolarization, if this graded potential is large enough to reach threshold at the trigger zone, and threshold is about -55 millivolts in most cases, then an action potential is going to be generated. What happens is our voltage gated sodium channels are going to open. Sodium is going to flow in. Then our voltage gated potassium channels are going to open. Potassium is going to flow out. And this is going to continue in, out, sodium in, potassium out, all the way down the axon. And that is our action potential. This is supposed to go down the axon. Harder to do when you're videotaping yourself. So when our action potential reaches the axon terminal, we have voltage gated calcium channels which are going to open. And then calcium is going to flow into the axon terminal, and this is going to trigger exocytosis of acetylcholine into the synaptic cleft. Now, if we go back to our axon here, if we added some myelin to this axon, then this action potential can move a little faster by jumping from node to node down the axon, and that is called saltatory propagation. If we don't have the myelin and that action potential has to travel down every portion of the membrane of the axon, sodium flowing in, potassium flowing out, sodium flowing in, potassium going out, then that is called continuous propagation.